Welcome to the second lecture of Biomathematics. In this lecture, we will be studying about graphs and functions. So, this is the second lecture where we will discuss more about graphs and more about functions. As you might remember, in the first lecture, we mentioned that we actually basically described the idea of functions, and we said that functions and graphs are related, and we also showed that many of the biological systems, we also discussed many graphs that you would get in a typical biology experiment. So, there are growth curves, there was molecular motors walking along microtubules and many other cases. So, in this lecture we will go and try and understand some of those graphs. So, the mathematical idea behind those graphs or the equations behind those graphs is what we will try and understand in this lecture. So, essentially in this, what we discussed last time is as seen in the slide. We said last time that experimental results, the relation between experimental results and graphs. So, when you do an experiment, what you do is basically you get a set of data and you plot this data as a graph. So, you get some, for example, like let us say you are measuring the length of actin as a function of free monomer concentration. Then the more the concentration, the more the growth speed is, the actin will grow faster. So, you can, for example, plot the growth velocity versus the concentration. So, you will have, when you do this experiment, you vary the concentration and you measure the growth velocity, or you could vary the concentration and measure the average length of the filament. So, depending on which experiment you are doing, you will be getting a table where concentration is on one axis and length or something else in the other axis. So, basically you will get a table with two columns, and you plot this data points that you get into a graph. The reason you are plotting into a graph is, as we said last time, is that a graph can convey much more information than a set of tables or a bunch of statements can convey, and it's quantitative. It can precisely say a few things about the system that we are studying. So, in this lecture, so as we said, there is some relation between graph and equation. So, every graph that you plot can be represented by an equation. So, this equation could be very complicated, but in principle every graph that you plot can be fitted or represented by an equation, and understanding that equation basically will help us understand the biological system in more detail. So, that is our aim. That is why we understand the equations. We want to study the equations and therefore understand the system, biological system of our interest in a better way. So, as we say here in this lecture, we will learn how simple equations can be plotted as graphs. So, we will take many simple equations and see how we can plot them and how can we connect this to a graph. So, graph and equations, that is what we are going to study in this lecture. So, as we said before, to plot a graph you need an x axis and a y axis. So, some value, some column which is x axis, which we will plot in the x axis, and some other column which we will plot in the y axis. So, there is a relation between this quantities in the x axis and the quantity in the y axis. For example, there is a relation between concentration and the length of actin filament. So, or in other words, there is the position of something is related to time. So, there is a relation between what we plot typically in a graph in the x axis and what we plot in the y axis. So, this relation is mathematically called a function. So, we said this last time, that function is essentially basically the relation between what we plot in the x axis and what we plot in the y axis. So, what is the simplest relation that you can think of? The simplest relation that you can think of is nothing but y is equal to x. So, if we define a function as the quantity is how a quantity in the x y axis is related to the quantity in the x axis. The simplest relation is basically y equal to x. Now, how do we plot this y equal to x as a graph? So, we will go and learn this today. So, let us say that you have a column with x values and y values. So, what are the simplest values? X equal to 0, y equal to 0. So, like when x is 0, y is 0, as you can see in the slide. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3. 4, 4, 5, 5 and 6, 6. So, this is a very easy point. So, like it is easy to understand, because for every x value, the y value is the same. So, this is the simplest function you can think of, and let us see how this is plotted. So, see the graph what we have plotted here. So, in the x axis we have x, which is 0, 1, 2, 3, 4, 5 and 6. In the y axis again we have y values 0, 1, 2, 3, 4, 5 and 6. Here the first point, the red square, field square, red field square are the points corresponding to this values. So, the first value x equal to 0, y equal to 0. So, the 0 0 is represented by a point here, and the next one, the 1 1 in this table. So, what does it mean is that for x value 1, correspondingly the y value is 1. So, this is what it means. For x value 1, the corresponding y value is 1. Similarly, for x value 2, the corresponding y value has to be 2. So, if you start from x equal to 2, which is this, the corresponding y value is 2. So, you can see the x value is 2, y value is 2. Similarly, when x value is 3, y value is 3, the corresponding y value is 3. As you all know, the way to plot a graph is keep putting dots for each pair of values, and you can connect them. So, there is some details about how to connect these values, which we will discuss completely in a different set of lectures, but for simplicity today let us connect just values with a line. So, basically what you will get is essentially a line. So, this set of dots connects like a line. So, y equal to x is a straight line. So, this is the simplest straight line you can think of, y equal to x. So, what does it mean when? So, as you can see, y equal to x is a line which goes from through 0 0. So, we learn the simplest graph and simplest function. So, what does it? What do we say here? Y is basically a function of x. So, typically this is showed in different ways in different books. Some books say y equal to x, some other lecturer would say y of x equal to x. Some other place you would see f of x equal to x. As you can see here, all this means the same thing. So, when you say y bracket x, what does it mean is that essentially is that y is a function of y depends on x. So, the y value varies depending on how x value varies. Similarly, when you say f bracket x, that means the f, the function, f stands for function, and the function depends on the x value. And how does it depend? It depends like x. So, this is the simplest way of saying. So, this is one way of saying y equal to x, or there are three different ways which you can see in different places. As you, for example, if you read a book, so the book would have written y of x equal to x, or some books would write f of x equal to x. So, all of this is essentially what we just saw, this curve. All of this means this curve. That means for a given value of x, there is a y value which is the same. So, now let us look at the next function. So, the next function is y equal to 2x. So, when you say y equal to 2x, what does it mean? The y value is twice that of the x value. So, let us look at this table which is here. For x value of 0, we have y value which is 0. When the x value is 1, y value is 2, which is double. So, that is what this 2x means, twice that of the x value. When x value is 2, the y value is 4, which is 2 times 2 is 4. Similarly, 3, 6, 4, 8, 5, 10. So, for every x value, the y value is 2 times that of the x value. This is what y equal to 2x means, and let us see how is it plotted. So, in the plot here you have x axis and y axis. So, for every number in the x axis, there is a corresponding y number. So, there are this vertical and horizontal lines. So, they basically, as you might from your school that how to plot a graph, and for every x value there is a corresponding y value. So, let us have a look. If you look at this, you will see that when x equal to 0, y is 0. For x equal to 1, y is 2. So, let us look at this graph. When x value is 1, if you go starting from 1, if you go up, you will reach the point which is corresponding to 2. Similarly, for x equal to 2, the corresponding y value is 4. For x equal to 3, the corresponding y value is 6. When x equal to 5, the corresponding y value is 10. Similarly, 6 has corresponding value 12, 7 has 14. So, basically we have put a dot in for each pair of these values and connected them. So, this is basically another straight line. So, y is equal to x is a straight line, y is equal to 2x is also a straight line, as you can see here. And in the coming classes, we will try and understand what exactly is the difference between y equal to x and y is equal to 2x, because this is important. But as of now, let us compare this y values, these two curves. So, let us look at the next slide, where we have compared y is equal to x and y is equal to 2x. So, the red curve here, as you see here, red is y is equal to, what is written on the top is wrong. What actually is that the green curve is y equal to x, as is marked here, and the red curve is y is equal to 2x, which is shown in the red. So, what is shown in the top is change the color code is not correct. So, y equal to x is shown in green and y equal to 2x is shown in red. So, as you can see, there is a difference. When x is 10, the y value is 10 for the y equal to x curve, and when x is equal to 10, the y value is 20 for the red curve, which is y is equal to 2x. So, as you see in the graph is marked y equal to x and 2x. So, you can see that the corresponding values for each of this x value, you can see corresponding x value and 2x value, and you can see that the red curve values are twice that of the green values. So, this is the basic difference between x. So, always 2x is larger than x, which we know, which is evident from the graph, except for x equal to 0 values. So, we will come back to these two curves and comparison more in the coming lectures, but so right now we understood that y equal to x is a straight line, y equal to 2x is also a straight line. So, in general y equal to 3x, if you plot, it could be another straight line, y equal to 4x is another straight line. So, y is equal to any constant times x is all a straight line, and all of them will pass through 0. So, in general, we could say that y equal to m x is basically a equation of a straight line that passing through y equal to 0, and when you say y equal to m x, where m is any number. So, 1x, 2x, 3x, 4x, it could be even minus 5x, m could be negative number, and we will see later how this, when m is a negative number, how does this graph changes. But for today, let us stick for m equal to, today we will stick for m values positive, we will only take m is equal to 1, 2 or positive values, and we can try taking negative values and try plotting it and see how it is different from the values we saw. So far we saw that y equal to a constant times x is a straight line. that is passing through y equal to 0. Now, let us see if you add a constant to this, let us say y is equal to 2 x plus some constant. How does it change? In the next graph you will see this. So, let us look at the next graph. So, next graph what we have plotted is y is equal to 2 x plus 4 is in the red dots represent a curve which is y equal to 2 x plus 4, and the green dot is the curve which we already saw, which is y is equal to 2 x. So, this is basically, this graph is basically a comparison between y is equal to 2 x, which can be written as 2 x plus 0, and y equal to 2 x plus 4, which is the red dots and the line points represents 2 x plus 4. So, as you can see, at x equal to 0, the green has value 0. On the other hand, the red has value 4. So, what does it mean is that the curve y is equal to 2 x and y equal to 2 x plus 4 are shifted. They are shifted by certain amount, the value 4 here. So, the difference between y equal to some constant times x and constant times x plus some other constant is that they are shifted by some value. So, the difference is only a shift, as you can see in the slide, as you saw in the slide. So, in general, any curve which is y is equal to m x plus c, where m and c are some constants, will remain a straight line. It is just that it can shift it from. So, it could pass through different values in the y axis, but it does not matter, whatever it be the values it take, it will be a straight line. So, that comes. So, since we understood functions like y equal to x, 2 x, 2 x plus 4. So, let us generalize this, y is equal to m x plus c. So, let us see the slide here, which says y is equal to m x plus c is equation of a straight line passing through y equal to c. You saw that m value as 1 and 2 and c value as 0 and 4. The previous slides where we saw, and that this is a general equation of a straight line. When x and y are related using this equation, the equation of the kind y is equal to m x plus c, we will say that y is a linear function of x. So, when the term linear itself means it is like going along a line. So, when somebody says y is a linear function of x, what they mean is that the relation between y and x, if you plot a graph, it will look like a straight line. When somebody else says a linear function, it only means that the relation is a straight line. If you plot a graph, you will get a straight line. When two quantities are linearly related, when you plot a graph, you will get a straight line. So, you could think of many examples where things are straight lines. For example, if you have a circle, the circumference of a circle is 2 pi r. So, the radius and the circumference is related linearly. So, you could take another example from biology. So, let us take an example from biology where a molecular motor is walking along a microtubule. So, in the cells, microtubules are typically starting from near the centrosome and going to the periphery of the cell. So, from the center to the periphery. So, microtubule will be walking from one end to the other end of the microtubule. So, if we plot the distance from the center to where the microtubule is traveling, where the motor is traveling, you will in some cases you will get a straight line on average. The average distance a motor traveled from the center is essentially, and if you plot with time, you will get essentially a straight line. So, let us look at the graph. So, what is plotted in the y axis in the graph is basically the average distance the kinesin traveled from the center versus time, and you get a straight line, and this equation is y is equal to v t plus some constant, where v is the velocity of the motor and c is the distance of the motor. So, this you have to keep in mind that this is not the instantaneous distance, but this is the average distance. What does it mean is that you do many experiments and look at the average value, you will get this straight line. So, this is the one example from biology where you have a linear relation between the position and time connected through velocity. We will come back to this example and understand this in detail in another context, in another lecture, but in this lecture it is enough to say that there are many functions there, y and x, two quantities in biology are related linearly, and when they plot you will get a straight line. So, you could think of many experiments you did where you got a straight line, and each of this case the relation between the quantities in the x axis and the y axis are linear. So, now that we understand the linear function, let us go and try and understand the next case, which is a quadratic function. So, what is the next case? So, once we understand y equal to x, the next simplest thing is y is equal to x square. So, let us go to the case y equal to x square. So, let us have a look at the table. So, when you say y equal to x square, what does it mean? For every x value, there is a corresponding y value which is square of that. So, the square of 0 is 0 itself, the square of 1 is 1 itself, the square of 2 is 4, the square of 3 is 9, the square of 4 is 16, square of 5 is 25. So, you have 5 values and 5 x values and 5 y values. The y values is basically the square of x values. So, now let us see how do we, if we plot this, how would it look. So, before seeing the plot, think about it. So, you had y equal to x as a straight line. Now, how would the y equal to x square would look like? So, think for a minute and then have a look at the slide here. So, what you have here is basically for every x value you have plotted the y value as we tabulated here, and what you would get is not a straight line, but a curved line. So, there is a curve, there is a curvature. So, the y equal to x square is slightly curved. We will compare soon the y equal to x and y equal to x square, but you can clearly see this curvature, and for every value of x you have a y value. So, y equal to 1 has 1, 2 has 4 and 3 has 9 and so on and so forth. So, you can see from the graph that y equal to x square is curved, it is not a straight line. So, as you see here, this is how we plot y equal to x square, and if we plot the negative part. So, we had only taken positive values for x, but if we take negative values for x, you would also get similar. So, for example, let us have a look at this graph. Y equal to minus 2, you have 4, minus 2 square is 4, similarly plus 2 square is also 4. So, this curve is essentially symmetric to about 0. If you go to the right of the 0 or left of the 0, there is the positive values or negative values, y values are the same. When y is 4, there are 2 points. When y is 9, there are 9 is just below 10, 9 there are 2 values, because minus 3 square is also 9, plus 3 square is also 9. For 16, minus 4 square is 16, plus 4 square is 16. For 25, there are 2 values, because minus 5 square is 25, plus 5 square is 25. So, essentially what does this say is that y equal to x square is a symmetric function, does not matter x is negative or positive, you have same values for y. So, it looks symmetric around x equal to 0. If you take x equal to 0 as a vertical line, and if you look both sides, it looks similar, is symmetric. So, this is basically simplest quadratic function is y equal to x square. Now, let us compare. So, we saw y equal to x and y equal to 2x, and we saw that 2x is large, goes above y equal to x in the graph. Now, let us compare y equal to x and y equal to x square and y equal to 2x square. So, let us have a look at this graph here. So, when y is equal to x square, you have this green line here, which this is y equal to x square, and the red line is y equal to 2x square. As you expect, y equal to 2x square goes above y equal to x square, because these red values are twice as that of the green values. For example, let us have a look at 3. When it is 3, x equal to 3, x square is 9, y equal to x square, the green curve, this point is at 9, which is just above 8, you can see here, just below 10. Then 2x square is at 18, because 2 times 9 is 18. So, this is at 18, and but at 0, both x square and 2x square are 0 values. So, starting from same point 0, they diverge, they go to different values as we go along the x axis. So, this is the comparison of y equal to x square and y equal to 2x square. So, now we learned two functions, a linear function y equal to x and a quadratic function y equal to x square. Now, let us compare, let us plot these values in the same graph, let us see what do we get. So, let us compare y equal to x and y equal to x square and see the graph here in the slide. As you can see here, the blue curve is y equal to x, is a straight line. The red is y equal to x square. So, the red is curved and blue is straight. And the interesting thing to note here is that below 1, so this is the value at 1. At 1, as you can see, x and x square have same value at 1. 1 square is 1 itself. So, these curves meet at 1. They also have same values at 0, because x 0 and 0 square is same 0. But between 0 and 1, the linear function, which is y equal to x, is larger than x square. Above 1, y equal to x square is larger than y equal to x. So, x square is larger than x when x is larger than 1, and x is larger than x square when the x is smaller than 1. So, at x equal to 1, they cross each other. So, this is an interesting point that you should keep in mind, that when you compare x and x square, function having higher power will have a lower value below 1. We will see this when we compare x and x square and x cube later, but always keep in mind, when x is less than 1, x square is smaller than x. This is as you can see, 0.5 has a square 0.25, 0.5 square is 0.25, and we know that 0.25 is smaller than 0.5. So, when you take any value of x below 1 and plot, the x square will be always below the x, smaller than x. So, this is one interesting thing, an important thing to keep in mind. This will be very useful at some stages later, but above 1, always x square wins, x square is larger. So, this is some interesting nice things about functions one should keep in mind, and this will be very useful as we go along. So, once we understand, as we saw previously, we had seen that we represent y equal to x, y equal to x square, we had two functions now, and as we saw previously that we represented this in different ways. We represented it as y equal to x, y of x equal to x, and f of x equal to x. Similarly, you can represent in a different way here, three different ways we can represent. Like in some books you would see y equal to x, y of x equal to x, f of x equal to x. Similarly, in the x square case also you could see, as you see in the slide here, some people would represent y of x equal to x square, f of x equal to x square, but as I said before, all of this mean the same thing. This all means that the y varies like square of x. So, the y or the function f varies like the square of x. So, this is some, as you see look different books, you would see different things, but all please understand that they all mean the same thing. So, now that we understand a quadratic function, think where all have you seen this square x square behavior, the quadratic function? Have you seen it somewhere? I am sure you have, and the simplest thing is area. Area is square of radius, 4 pi r square. It is a formula which you remember from your school days. So, for example, the surface area of an organism. The surface area means if you have a spherical organism, like the surface area is basically 4 pi r square again. And this is important because as you see here, the basal metabolic rate, for example, of an animal is proportional to its surface area. So, basal metabolic rate will be a quadratic function of the radius. The more the radius, the metabolic rate could differ. So, it differed quadratically. Similarly, the energy stored in a spring like molecule is half k x square. So, where the x is basically how much the spring is stressed. As you can see, the more, as we saw here in the previously earlier, x square had a behavior which like increase like a curve. So, as I can draw here, we saw that when we plot x square, it was increasing. So, this is let us say half k x square. So, what does it mean? The more stretching is x is the stretching, the more you stretch the spring, the more energy you need to give to stretch the spring. So, the energy of, so this is true for any molecule. If you take any protein and stretch the protein, you have to spend more energy. So, this is basically the spring analogy is very useful for different biomolecules, and the energy of stretching a biomolecule is quadratic function. So, the elastic stretching energy is a quadratic function. So, this is like metabolic, the basal metabolic rate and stretching energy are two examples of a quadratic function. So, now we have seen this x square, and the next simplest function is x cube, and let us try and see how, if you plot x cube, how would it look like. So, have a look at this slide. So, what you have plotted here is basically y equal to x, y equal to x square, and y equal to x cube, and the red line y is equal to x, the green line, the green curve is y equal to x square, and the blue curve is y equal to x cube. And as you can see here, at 1 all of them meet, that means the square and cube of 1 is 1 itself. Below 1, highest, the x is larger than x square, the red is above green, x square is larger than x cube, that is the green is above blue. So, as I said previously, x square is larger than x cube when x is less than 1, but above 1, as you can see, the green gets larger as we go for larger and larger x, the blue is growing much faster, which is x cube, and green actually grows faster than the red, which means x square is growing faster than x. So, for example, for the value 2 here, red has a value for n is x equal to 2, y is 2, for y equal to x square it is 4, for x cube it is 8. And the interesting thing you should note here is the way it grows much faster. So, when I say the blue is growing, when I say blue is growing faster, what does it mean when I say, what does it mean to say grow is an interesting thing, and we will come and discuss in another lecture what does it mean to say it grows faster. It is related to some interesting mathematical property of a function, and we will discuss this in the coming lectures. But just look at this graph and remember, let us have a look at this graph once more. So, just remember from this graph that x cube grows faster as we go along this. For larger and less x value, x cube grows faster, x square is not that fast, but it is faster than x, and x is the slowest. So, when I say faster, growing faster, there is some strict definition of this mathematical definition, which we will come and discuss another day. Now, we got introduced to this the cubic function. So, the cubic function is 4 pi. So, what is the simplest cubic function that you can think of? The volume. So, the volume of a sphere, for example, is 4 by 3 pi r cube, we all know. So, that is the simplest function. The cubic function is basically 4 by 3 pi r cube, which is volume of an organism, for example, having radius r is 4 by 3 pi r cube. So, you could think of other examples where the biological property goes like a cubic function. So, now we understand x square and x cube. We could also imagine x power 4, x power 5, x power 6, x power 7. So, you could now that we are familiar with this, you could plot all of them, and you could also imagine various combinations of all these functions. So, you could define a new function which is x plus x square. So, let us have a look at this, a new function here. Let us y is x is what we learned. We also learned y is equal to x square. You could think of new function which is x plus x square. This is a different function. You could think of another function which is x minus x square. So, you can add and subtract these functions and you will get a new different function. So, one can imagine, then now you could imagine the same thing with x cube. So, let us say you have y is equal to x plus x square minus x cube, or you could say x minus x square plus x cube, or you could say y is equal to x minus x square minus x cube plus x power 4. So, one could imagine various combinations of all these functions, and it turns out that, as you can see here, as you will see in this lecture soon, that most of the experimental graphs you get, when you do an experiment, you get very complicated graphs, which is very different from what you saw now. X square are simple graphs, but you get a complicated graph, many complicated graphs, and it turns out that most of these graphs can be represented as a combination of this x square, x cube, x power 4, x power 5. Just like we saw, we can appropriately add and subtract these functions, and you can get any other function. So, this is important. This is very interesting feature so this is very important to remember, that any graph, almost any graph that you get can be obtained by adding or subtracting this x square, x cube functions in different ways. So, what people call it linear combination. So, the combination of x square, x cube, etc. will give you another function, and most of the function that you see in experiments can be represented as a combination. Also, many natural processes that you see can be fitted with this kind of combination of these functions. So, one very simple and very commonly seen function is called exponential function. So, you might have heard of it, you might have seen it somewhere, e power x is called exponential function. So, this exponential function essentially can be written as some combination, a series of this x, x square, x cube, x 4 and all of that. So, let us see how this exponential function is defined. So, this is, as you can see here, exponential function e power x is basically defined as 1 plus x square by 2 plus x cube by 6 plus x power 4 plus 24, x power 4 divided by 24 plus x power 5 divided by 120 plus so on and so forth. So, you can, this is an infinite series. So, you have to sum x power 4, 5, 6, 7, 8, 9, 10, you have to keep summing. So, if you just keep summing, you will get this value of e power x. So, where do we stop? So, in the coming slides, we will see where to stop this. So, do we have to sum till infinity? Is it practical, or can we stop at some point? We will discuss this in the coming slides, but as you know, e is just a number, it is a irrational number which is 2.7 approximated 2.718828, so on and so forth. So, and e power x is basically this defined in this particular fashion as a combination of this functions x, x square, x cube, x 4, etc. And this values coefficients 1 over 2, 6, 24, etc. And just for now, just remember that there is some combination, some particular combination of x, x square, x power 4, etc. And we will try and understand later that where this combination comes from and so on and so forth. But for now, it is sufficient to understand that e power x is defined in this particular fashion. E power x is defined as 1 plus x square by 2 plus x cube by 6 plus x power 4 divided by 24 and so on and so forth. So, now let us see how, if we plot this function x power e power x, how does it look like. So, let us have a look. So, here is what we have plotted is e power x in the y axis and x in the x axis. So, as we did previously, we can make a table x in the x in one column and e power x in the other column, and you can plot these points and connect them together. That is what we have done here. So, each of this point represents some pair of values. For example, when x equals 0, e power x is 1. As we can see, as we saw in the previous slide, if we put x equal to 0 everywhere here, all of this term is 0, 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 you have just 1. So, at x equal to 0, e power x is 1. So, that is why when x equal to 0, you have e power x is 1. And you should remember, whenever you see a graph, you should remember two things. At the two ends, what are the values? So, x equal to 0, it is e power x is 1. As x is equal to infinity, or as x grows, e power x grows. It's a curved, it's not a straight line, and you can see that it is increasing rapidly. So, we will see later that is it larger than x or larger than x square and so on and so forth. So, as we saw, e power x is basically defined as an infinite series. Now, let us ask this question, where do we stop this series? Can we stop at x, x square, x cube? Is it correct to say that e power x is 1 plus x, or is it correct to say that e power x is 1 plus x square by 2? It is not correct always, but at some cases you can approximate e power x with 1 plus x and so on. So, let us look at this next graph here. So, what is plotted here is basically in the y axis you have two curves. So, green and red. the red is y is equal to 1 plus x, the green is y is equal to e power x. So, when the 1 plus x is a straight line, it is a linear function, e power x is not a straight line, it is a curve. And so, as you can see very close to 0, they have same values. So, this red and green meet close to 0, but as they go away from 0, they diverge. So, this goes like this and this x 1 plus s goes in this fashion. So, what does it mean? It means that close to 0, 1 plus x and e power x has same values. So, it is okay to approximate e power x as 1 plus x when x is very close to 0. So, when x is very close to 0, one can say e power x is approximately equal to, that is what this sign means. This sign means approximately equal to. The e power x is approximately equal to 1 plus x when x is very close to 0. Now, if we take little more values like 1 plus x square by 2 plus x cube by 6 and so on, what do we get? So, in this series, so we saw that e power x is a very long series, infinite series. If we take more and more terms, we took 2 terms, 1 and x, 1 plus 2 terms we took, and we saw that only when very close to 0, e power x and this 1 plus x matches, 1 plus x match. When they are far away from 0, they diverge. So, now let us take a few more terms, 1 plus x square by 2 plus x cube by 6 and so on and so forth, and see whether it matches when you go little more away from 0, whether the value their values are same or not. So, let us have a look at this graph. So, what shown here is that the green is e power x, the red is here 1 plus x square by 2 plus x cube by 6. So, this function, what is shown in this red ellipse, this is what is plotted here as a red line. 1 plus x square by 2 plus x cube by 6 is plotted using a red line, and e power x is plotted using a green line. As you can see here, below 1 pretty much almost all the places they match. The function e power x and this 1 plus x square by 2 plus x cube by 6, they match with each other close to 0, and above 0.5 also they match. Like very close around 1 they start diverging, and e power x goes faster than the sum of this quadratic, cubic plus linear functions. So, 2 things we understand from here is that the more terms we take, the approximation becomes better. So, one could write again that e power x is approximately equal to 1 plus x square by 2 plus x cube by 6, and the approximation is better here because we took more terms. Previously, we had only 2 terms and here we had 4 terms. So, let us compare these 2 approximations. So, have a look at this graphs, and in the x axis, in the left side we have this 2 terms 1 plus x. So, the approximation with 2 terms, and in the right we have approximation with 4 terms 1 plus x square by 2 plus x cube by 6. And you can see that on the right side is much better than what you see on the left side. So, what you learn from is that the more term you take, the function becomes more closer to the e power x. So, if you take all the terms, you get exactly e power x, and you also see that e power x is larger than the higher the x, the e power x wins. E power x is faster than any of these combinations. Like if you take this sum, e power x is faster, grows faster, is growing faster in a faster pace. So, we will come and see what does it mean to say that it is faster, slower, etc. But what we saw so far today is basically we studied, we saw some simple mathematical functions like y equal to x, y equal to x square, y equal to x cube. We also saw that the combination of x square, x cube, x etc. gives us some other function, and some well known mathematical functions like e power x can be represented as a combination of these functions. And in the coming lectures, we will see how this combination give rise to some very well known functions in mathematics. So, today we will stop at this point, and in the coming class we will take some biological examples, and we will see that how this example biological functions that we plot as typically graph in experimental data can be represented as a combination of these functions. And we will learn many more interesting functions, which is very important, relevant in biology, and we will discuss their relevance. So, to summarize, the relation between quantities that we plot in the x and y axis is called a function, and we learned many simple functions like x, x square, x cube, etc. And we also saw that some known functions like exponential of x, e power x can be represented as a combination of simple functions like x, x square, x cube, etc. And in the coming class, we will see many more interesting functions and see how they are related to some of the known biological experimental data. So, some experimental data we get from biology experiments can be represented by as a combination of these simple functions, and we will see them in the next class. Thank you.